organizers of this amazing special year. This is kind of my chance to say it in public, so thanks for having me here. It's been great professionally and also for my family, so it's a great thing, this institute. So let me start by reminding everybody, I'm probably the only one who remembers, so it's a good reason to remind you of a question that I asked at the open questions session in Sde Boker at the very beginning of the year. And for those of you who didn't see it, that's fine. At all, just here's a sort of a definition. If I have a word over some finite alphabet, so sigma throughout this talk is going to be some finite alphabet. I have a word of length n. I'll let w bar be its reversal, and I'm going to define the sort of palindromic distance of w as the 1 over n, so you normalize by the length of the Hamming distance between w and its reversal. So you just write down w, on top of that you write down the reversal, and you look at how many places they're different. And at the workshop at the beginning of the year, I mentioned the following fact, that you can take the infinite ternary tree, and the degree is really not important, but take the infinite ternary tree, and you can label all of its edges with some finite alphabet. So there's an alphabet that's a finite, so for any fixed delta, there's a finite alphabet, such that whenever you kind of take a simple path through the tree and you read the word that you encounter as you go across that path, it's very far from palindromic. Okay, so the distance between w and w bar is at least a 1 minus delta fraction. It should be as close to 1 as you like of its length. Okay, so it's a theorem, and if you haven't seen, if you've seen sort of, hopefully everybody sort of knows the probabilistic method. So certainly a random labeling of the tree doesn't satisfy this. But there are standard methods that will give this to you. So this is not calling it a theorem, but it's sort of a corollary of things that we all know or teach.
Whose theorem is this?
So, I guess it's mine, but it's not a theorem. This you can get with standard methods. What's going to be interesting is that there's sort of 3 different proofs I know of this type of statement, and they each give you different things. So if you want this version, this kind of way of doing it, you would probably go through the Lovas local lemma, but there are better proofs for other purposes, which maybe I'll come back to. And just for future reference, if you sort of look at the dependencies of the parameters, when you want to get distance close to 1, delta is small, then the alphabet grows sort of exponentially in that. Yeah. Okay. So the problem wasn't this, of course. So the problem was to explicitly build such a thing. So what do I mean? So I'll talk a little bit what I mean. But and by the way, so this is true for every delta. But for explicitly building, you just give me it's not clearly equivalent. So just give me any delta less than 1. I'll be quite happy. Okay. So we don't. So this is the problem, and I still don't know how to solve this problem. Okay? But there's been progress, which is what I'm going to tell you about. So why am I asking this question? So it's a not very disguised version of something that matters for interactive communication. And so now we're going to think of, so here's the ternary tree except at the root, and I'm going to think of it as directed, and the direction is going to play a role. So now we call it the infinite binary tree, and every vertex here has sort of an address, which is some binary string, and you sort of go left is 0, right is 1, something like that. And I'm going to think of the tree as a metric space, but I only care about distances between vertices that are at the same depth, so x and y. In this definition, I write distance 2 because that's the distance to their least common ancestor. Okay, so that's going to be my notion of distance. It's closely related to the actual tree distance, but I just don't care about vertices that are at different levels at all. All right, so so that's this tree distance, and the property that we want is that we should label. So in this now, from now, it's sort of easier to think about labeling the vertices, but the vertices and edges are in one-to-one correspondence, except at the root, so it's the same thing. So what we want is to label the vertices of the tree, again, by some finite alphabet. And now you can see in such a way that for whenever you have such a pair of vertices and they split, some L number of levels ago, before, you went down, and then they split, and there were sort of L levels after they split, that the Hamming distance between whatever string you read here, going down here, which would be the string CA, and the string, the word you would read going down the other way, which would be BB, okay, that Hamming distance should be proportional to the actual tree distance. And this is, in some sense, not the right way. The caption is sort of wrong. You should really just think about the labeling since they split, since they obviously share them. Okay, so what we're essentially asking here is that the palindromic distance, the what you see for well, just think about it like this, not with palindromes, but the distance between the words should reflect the actual distance in the tree. Okay, so it's an embedding of the tree into the labeling of the tree in that sense. Okay, so this is, and when we have that up to constants, we'll call this an asymptotically good tree code. This is following the usage of the phrase asymptotically good in electrical engineering encoding theory. Okay, so we want the alphabet size to be finite, and we want it to preserve distance up to a constant factor, and that's exactly what this is saying here. Okay, if they split S levels ago, then the distance should be at least fraction 1 minus delta times S. All right, so this is what we want to build. So here's the thing. There's this. Actually, I'm moving along very fast. I've hardly been interrupted at all. So I'm not expecting that to continue, and therefore I did the following thing with this talk. So there's a saying of Ron Graham that every talk should have a theorem and a joke, and they shouldn't be the same, right? Yeah, so it's true. So I hope my standards for jokes are lower than my standards for theorems. So I'll figure that one out. Okay, so there's a joke. There's a really good joke because it's not mine. It's due to the great cartoonist Bill Watterson. That gives a wonderful explanation about interactive communication theory. I'm really worried that I'm not going to have time to show it to you. And I figured if a theorem, one of the two things have to go, I should at least leave in the theorem, I think. So I did. So I have tossed all of the slides explaining the whole motivation for this business, which comes from Bill Watterson, the author of Calvin and Hobbes, to the appendix of the talk. And I'm only going to give you one slide on the why. And if we have time, we can read the Sunday comics. So here's why we want. No. I'm saying I'm not going to even satisfy Graham's minimal requirements. No. Half. I'm only going to satisfy half of it. Maybe not even. Okay. So this is just one kind of conventional slide. Why do we want these things? And then we'll just talk about the combinatorial object. Okay. So the reason we want them is because they are the sort of necessary combinatorial component of the interactive version of Shannon's coding theorem. So maybe everybody knows, but let me just say, what does Shannon's coding theorem tells you? There are two parties to the communication, and this is how all communications work, have worked for the last 67 years. Alice has some message, it's a binary string of length n. She would like to send it to Bob, but there's noise on the channel. We have two standard models for noise. Either there's adversarial noise, so the adversary can come along and he can, like, every some fraction of the bits, up to some fraction of the bits he can flip. So that's one model for noise. That's the adversarial model. There's a random model for noise, which is every bit gets flipped with some probability p bounded away from a half. And then, so there's two different standard noise models. There's some others, but and Shannon in 1948 invented, sort of really this notion of, essentially invented the notion of error correcting codes, or what I'll be calling block codes. So in block codes, they're block codes because when you come to encode the message, you take the whole long string as a block and you encode it as a whole nother block. And here's his theorem. There's some constant such that for all n large enough, there's a mapping, which we'll call ECC for error correcting code, from binary strings of length n to, you have to slow down by a little bit, so that the rate would be 1 over this constant, CECC. And for reasons of my own, I want to put the exponent here, n over 3. You can always move these constants back between here and here, so I'll do that. That achieves distance 5/6. Okay, I mean, the theorem's more general. I'm quoting it kind of in the form that I want to use it later. Okay, and it achieves this distance between any two code words, and you can see that when you have that property, you can sort of deal with either of these kinds of noisy channels. Yes? Okay. So the story that I'm not telling you is why this is sort of not enough. We do actual communications, not like in a talk like this, but in actual conversation. They're very highly interactive, and that's necessary. Okay, so if you want, we know from theory of communication complexity that if you have a problem two parties are trying to solve, and they want to solve it efficiently in terms of number of bits exchanged, that they sometimes must have, sort of send just one bit back this way and then one bit back and then so forth. So this is a theorem. And so these kinds of Shannon codes aren't good enough because you sort of don't have a long block available for encoding. So how do we nonetheless protect them efficiently against channel noise? So there's a theorem, which is now about 25 or so years old, that says we can actually do this. So there is a deterministic protocol that when you want to simulate, you have the protocol that would have taken n communications, but it was sort of interactive protocol. Alice and Bit are exchanging bits sort of in real time. You want to simulate that despite noise on the channel. Then they can do that with no error probability at all in the adversarial case, or with exponentially small error probability in the just random case. So it's exactly like in the Shannon version. That there's a way to do this. Okay, so this is a theorem, and there's sort of two things you need for this theorem, and one is this tree codes that I've already sort of defined for you, and the other is some simulation protocol. So it doesn't. It's not. There's a whole separate story which has to do with how you use the tree codes, and there are several versions of that. Things have gotten better over the years, which it's a whole other story, or several other talks or something. Okay, so I'm not going to touch on that at all today. So the question is, what do we know about building the underlying combinatorial object, these tree codes? So now I have to say what I sort of avoided saying before in the context of the palindromes. What do we really mean by constructing these things efficiently? So this tree is the depth is n, so that's sort of the complexity parameter we're working with. That's how long the conversation is supposed to go on for. The tree is a binary tree, so it's exponentially larger. But we don't actually want to build that whole thing, right? We don't really need it. We only need like parts of it that like Alice and Bob are using for their. So the right definition of constructing such thing is I tell you the address, some vertex in the tree, and you respond to me with the label at that vertex in time polynomial in the depth of that vertex, or in the depth of the whole tree. For linear, you can, but that's the complexity world that we want to be in, not building the whole tree. Okay. So now let's say, what do we know about tree codes? Okay. So it's trivial and basically useless to get a tree code if you allow. You could just label every vertex with its whole address, and then once two paths have split, they're never going to use the same addresses anymore. But of course, that requires n bits to label a vertex, so that's a horrible solution. there's a less horrible but still extremely elementary solution that uses a polynomial size alphabet. Okay, and it's just, you have to do some things, but you could assign this to students as an exercise if they'd seen error correcting codes. And so this would give you communication rate 1 over log n. So instead of like the Shannon theorem where you had all this noise and you only had to slow down by a constant factor, here you would slow down by a factor of log n. Okay, so that's and to tell you the truth, this elementary result, is the best we've had since 1994.
But you don't know that you cannot do it with a polynomial number with the alphabet polynomial.
This is alphabet polynomial, is it?
I mean with the
Constant.
constant rate.
No, I not only do I, no, that's the open question. What I'm not going to talk about today, unless there's turns out tons of time, I even have a conjectured construction that's not the result I'm talking about today that might work, but depends upon I'll get to this. But that's the question.
So what, you
Okay,
believe it's possible
I believe it's possible.
in polynomial,
I believe it's
polynomial
possible.
alphabet to achieve.
Constant alphabet. I believe it is possible with a constant size alphabet where you would compute the label in time polynomial in the depth of the tree, or even the depth of the node. Even better. That ought to be possible. That's what's been open since 1994.
That means the communication rate is.
That would give you a constant communication rate, and we know that it's existentially possible. I mean, as I mentioned, these theorems, three different proofs I can give you.
You know that it's.
So these trees exist. Okay, these tree codes exist with constant size alphabet.
The theory you gave in the first slide was with an exponential size.
It was exponential.
1 over delta.
It was exponential in the distance parameter. Forget the distance parameter. Make the distance parameter constant. So that exponential is not.
Delta equals 0.7.
Yeah, delta is 0.7. The distance is 1 over a million. I'm already a very happy man. Yeah. I just wrote down that because we're gonna come up, but yeah, that's not so important. Well, it's less important than right. So the computation time can't possibly be constant. I mean, you have to read the address of the label, but the label could be constant, and that's the outstanding open question, which we still haven't solved, but we've made some progress. Okay. So if everybody is okay with me, so what we're talking about today, so this is elementary. It's been, in terms of things that we can prove, it's really been the best that we know till today, till this year. Okay. There are weaker objects, a variety of weaker objects that we know how to construct effectively. There's some clever trade-off between computation time and size of alphabet, but and then there's this thing. Okay, then there's this thing I alluded to. Why do I think this should be possible? It's because well, first of all, I'm an optimist, but second of all, the better reason is actually a proposed construction that proving it works seems fairly hopeless. But there are people in this room who know more about the needed ingredients than I, so I'm hoping they'll. Okay, so. So, pardon?
That's sort of the conjectures of the pseudo-randomness.
The conjecture, yeah. I mean, it's the fact that a variety, you have these bounded exponential sums is one way of expressing that the it's a pseudo-random. It's a more or less a algebraic or combinatorial pseudo-random, not a computational pseudo-randomness property of those. But that's a different. It's a different. Okay, so now I'm going to tell you what the main result I am going to show you today, or hoping to. So you remember I gave you this quantification before. The existence proof shows that the alphabet size is going to be bounded by exponential in 1 over the distance parameter. What the main result today is that instead of this polynomial in n, which is this elementary construction from 1994, we're going to go down to polynomial in log n in the construction I give you today. So it's going to be an exponential improvement in the alphabet size. Okay, that's the. Okay, so here exactly is the theorem statement. You fix any delta. We'll give you the binary tree code into an alphabet. We'll get the distance 1 minus delta that you required, and the alphabet size is going to be polylog in n, where of course the exponent of the log depends upon what distance delta you asked for. But okay, so that, and I think I should be able to show you the whole thing. Okay, so the rate, as the consequence for communication rates, is that you slow down, so you don't achieve what you would in asymptotically good code where you should slow down by a constant factor, but you slow down by 1 over the log n factor instead of 1 over log, which is what we knew. Okay. And the code is I mean, I just want to say, because this will also come up when I describe the construction to you, the code has a lot more uniform structure than sort of implied by the theorem statement. Somehow you're going to be like writing in several parallel tracks. So you think of printing out the label of a vertex. There'll be like a bunch of registers or tracks, and you just are going to do the same. The first few tracks are just going to repeat down. As no matter how deep you go into the tree, and every time the tree gets deeper by going from like n up to n squared, you'll have to add a new track. So, but what's happening in those first tracks will just kind of repeat itself periodically. So there's sort of no. It's not some messy thing. There's fairly. Okay. And each of those tracks will be a constant number of bits. Okay, so just an outline of how this is going to go. First, I'm going to describe to you kind of a tree codes that label vertices with integers. So this doesn't help us directly get finite alphabet size, but it lets us do things sort of lets us work freely sort of with polynomials. Then we're going to convert to a finite alphabet scheme. We'll get a weaker object than tree codes. They're going to be these things I'll call lagged tree codes, because they won't immediately give you distance properties. There'll be like a time lag before you get the distance property that you want. And then finally we'll have to pay this log n by sort of fitting together several of these lagged tree codes. Okay. Okay. So let me start with the sort of algebraic sort of essence of this method. The first thing we're going to do, so in a binary tree code, the input alphabet is 0, 1. As you go down the tree, you either go left or right. And say something. We're going to now sort of, in a very natural way, and this is going to be really essential, take, as the input alphabet just being the integers. Okay? And of course, as I already said, the output alphabet will also be the integers. So, and we're going to be reusing the like, if there's one thing you need to know about coding theory, it's read Solomon codes, right? Which is works as follows. Just so I don't really know what people know. So, how do you encode a message in read Solomon code? Is again, you can think of this. Well, you can do this over any field, but your message, you just think of your message as a bunch of field elements being the coefficients of a polynomial, so some polynomial a of x, and then so there were n field elements, and then you go and you encode them in 1 plus c times n field elements by just evaluating the polynomial at a number of points. Okay. You can do this, and the field just has to be big enough to give you enough different evaluation points. And the distance property just comes from the fact that polynomial has no more roots than its degree, and so that bounds the number of places where two polynomials can agree, and so you have to be different in at least c n. Two distinct code words have to be different in at least c times n positions here. Okay. So this, of course, we can't use directly, right? Because here, in order to evaluate this polynomial at any location, I really need to know the whole list of coefficients, except maybe at 0. Okay, so I can't, this is not going to be online, this won't give us what we want, but we're going to use we're going to have to do things a little differently. So the first thing we're going to do is, implicitly, a moment ago we were using a certain basis for the polynomials, which is just the basis we usually use, which is just the powers of x. There's a nice different basis called the Newton basis, which uses sort of the binomial. So the polynomial is x choose I. So you still get get 1, you get x, but then you get x times x minus 1 over 2, and that's the sequence of polynomial. It's a really nice basis. So here, if I have a polynomial gamma of x, this will be its expansion in the Newton basis. It's a nice basis. One thing is nice about it is it's not so important for what we're doing, but just to say it's an integer basis. So the coefficients, the gamma sub i's, are all integer if and only if the polynomial is integer everywhere. Okay? That's a pretty nice property. It's not that essential to us, but it's something nice to know. It's not true for the standard basis. Now here's the thing that we really need, which is the roots of the ith basis polynomial are the integers 0 through I minus 1, okay, which is obvious from the expansion of the, okay. So but that's essentially. And what this means is that, for any value of I, the evaluations gamma of 0 up through gamma of j determine the coefficients gamma naught through gamma j and vice versa. So if I want to know the value of the polynomial at the points 0 through j, I only need to know the first j, or j plus 1, I should say, coefficients of the polynomial, because all the higher terms are 0 on all those points. Okay. So now this alone is not. So you could say, okay, let's do Reed-Solomon this way. What's the difference? So you could say my message is gamma naught through, and then I evaluated the first. That's not good enough. That's a rate 1 code. So you can't possibly get distance condition from that. But there's an obvious fix, which is send the gammas and send the evaluations of the polynomials on those first points. Okay, so we can get a totally natural way of getting a rate 1/2 code out of this, which is I tell you the coefficient gamma naught, and then I tell you gamma of 0, and then I tell you the coefficient gamma of 1 and the gamma of 1, and so forth. Okay, so that's a not natural. And it'll be a little more convenient actually to say things the other way around, which is suppose that the message is a stream of integers z0, z1, and so forth. And I'll go the other way. I will I'll incrementally define the coefficients of the polynomial to interpolate the first at time t, the first t values of the polynomial. And so what I'll send you at time t is z sub t and also gamma sub t. Okay, and if you think about it, okay, well, I'll just say two things. So first of all, this is certainly a linear mapping. It's just some interpolation theorem. Okay, and at any finite, so somehow eventually what we're looking at, in the limit is not a polynomial; it's some power series. But at any finite time, you have a polynomial, which I'll call gamma sup t, which is just this expansion up till t of this polynomial.
So far you only used upper triangularity.
That's right. That's right. That's right.
Upper triangularity and ones in the
And there's ones on the which wasn't even that essential, but it's true. But it's true. Yeah.
to invert the matrix.
Yeah, which is equivalent actually to that thing about it, so it's an integer basis for them. Okay. Now, just to point out one thing, which is, I think like these things might be creeping up on you, and everything's. So there's one thing to notice, which is that there's a kind of grandfathering, or I don't know how to say, or hereditariness, which is that, if j is less than or equal to t, then z sub j is always what gamma t tells you the value at j is, right? So somehow, the later polynomials always respect the earlier values of the polynomial. So that this is whereas the kind of their predictions about what would happen in the future vary, widely. Okay, so just to read it out, maybe put in a little more explicit thing. Here's the tree code proposal. It's over Z, so this really isn't a tree code yet, but it's this kind of a coding over Z. Is I have an input stream, Z0, Z1, and so forth, and I get my, at every time step I send you what's in one of these columns. So a pair, Z0, and then this new coefficient gamma naught that I just figured out, and so forth. So I'm not going to, sort of rate 1/2 in some sense, and I'm not going to talk. I will get back to the size of the integers. It's essential, but not right now. And first of all, let's see if it has a distance guarantee. Okay, where distance we mean sort of Hamming distance over the integers. So again, this is a linear code, and whenever you have a linear code, you don't have to talk about distance between two code words. You can just talk about distance to 0. So, and of course, the 0 stream encodes as all zeros. So, so here's what we're going to do. So I'm going to look. What I have to do is I have to tell you this. Suppose I have an input stream of z's, and sigma is the first place where it's non-zero. Okay. So up till now, everything has been outputting zeros, and now from now on, we get what we get. I don't know what we get, right? So it depends what the stream is, but this is the first time it was non-zero. What does distance guarantee delta mean? It means that if I go, from sigma up to times sigma plus m, in at least this so there's m plus 1 positions here, at least fraction delta of them, the pair is non-zero. Okay, well, at least one of them is non-zero. Sorry. Yeah, okay. So here's just now I want to rephrase all this as a statement about the polynomial gamma sigma plus m, right? Because all of the values in this table are actually values of the polynomial gamma sigma plus m, if you would go. So let's make this a statement of that polynomial. Again, sigma is the first place where this polynomial has a non-zero coefficient. Right, so the gamma sigma here is not. These two first entries are equal to each other. And this is the first place where something is non-zero. So I'm going to look at the density of non-zeros downstairs in the coefficients and the density of non-zeros in the evaluations. So I'll have two different densities, sort of densities of the gamma stream, and this is the density of the z string, the fraction of non-zeros upstairs. And there's a simple equivalence that says that the actual distance that we get, namely the distance on pairs, is somewhere between the maximum of those two numbers and their sum. So it sort of doesn't matter whether I look up to a factor of 2. It doesn't matter whether I look at pairs or individual entries. And the thing that we're trying to show is some kind of what people like to call an uncertainty principle, that we have a representation of an object in two different bases, and not both of those can be sparse. So if delta gamma is small, you're sparse in the coefficient basis, then you have to be not sparse you have to have few roots. The polynomial has to have few roots in this segment. And okay, so you can ask, is this something you should expect? Okay. Is it made clear? I mean, it should be very, yeah. So I have to say, one of the reasons that it took us a while is it really doesn't seem like a reasonable thing to expect. Okay. So I'm going to give you an example. Take the polynomial. So a constant. So so this is something where the first non-zero coefficient is just at 0. So we'll start off right away because it's not really that important. So well, it's going to be a constant plus some large number times x choose n. So this is a polynomial with sparsity or density of coefficients 2. It's only got 2 non-zero coefficients. So we would have to. So we're sort of arguing that it should have very few roots. When you look at 0, 1, 2, up through n and so forth. Yeah, it should only have like 2 roots. That's all. Okay, ideally. And if you look at a polynomial, here's an example of a polynomial like that. Take -1 plus 5,000 times x choose n, and I dutifully plotted it for you, and I can show you where the roots of this polynomial are, and here's where the roots of this polynomial are. There's one, that looks like an 8 to me. That looks like a 7 to me. That looks like a 6. That looks like a 5. 4, 3, 2, 1. Which is no surprise because that's where the roots of x choose 9 are.
Let's shift it.
I just, I hit it, you know, I put a -1, so I moved them a little bit, but,
You need x to 9 not to be 0, but to be 1/5,000. So this is what you're asking, right?
I need what? I need,
X choose 9
yeah,
is 0 for x equals 0 up to 8.
that's right.
Now you don't want it to be 0, you want it to be 1/5,000.
Yeah, that's what's going to wind up being, yeah.
Move a little bit from the 0.
So, but remember, what I really need for my code to work is I really need to say it. I really need that to be true. I really need to, I really need to be, even though it's below the pixel resolution, I really need the root not to be at 8 and not to be at 7 and not to be at 6. Okay, okay, that's what we need. So, so it's a strange thing. It's certainly not. I don't know. To me, it's a strange thing to ask for. So we have to show that somehow the number of roots, you know, after the split out to infinity, at integers. All of those roots, or all of them except however many coefficients there were here, are not going to be at integers. Even though, as this example shows you, they can be, you know, below your. Okay. So, so it's true. Yeah, here it's a kind of, I don't know, I love this lemma. So here's what it says. So here gamma is some polynomial, and we'll say, you know, suppose this polynomial has some number s of coefficients in the new.
Just, I mean, perhaps
Yeah.
you know, but I'm not sure that this comes close to this notion of funomial.
Yeah.
Yeah. There is a funomial. There is a very witty knows about this more than I do. There is a rich theory of normally you say that a polynomial is small if its degree is small, if the coefficients are small. But there's also a rich theory speaking about the small support, only few coefficients. Here, although this is not in the normal way, the regular basis, but in the Newton basis, that's the same concept.
Yeah.
So
Uncertainty.
Right. Maybe as an asterisk. I mean, you want to mention this result of Rui and Tao, and yeah. But maybe we won't mention it now. There are results like this in the standard basis, which, time permitting, after the Bill Watterson stuff, we'll get to. You know? Okay. Yeah. So there are, right. Okay. And there's actually some mathematical commonality. Sigma is again the first place where gamma has a non-zero, the lowest the index of the lowest non-zero coefficient of gamma. So gamma is a polynomial. It has the form. I saw a piece of chalk escaping. You know, gamma of. Oh, actually, well, actually, it kind of says here. So gamma of x is gamma sigma. So here, sigma is sigma 1. Okay, sigma 1 times x choose, you know, sigma 1, you know, plus blah blah blah, all the higher things. This is the lowest place. So this is where you can expect things to start being this is where we start making the distance requirement. Okay, so sigma is the place where we have the first non-zero coefficient. It'll also be the first, you know, at that point, gamma sub sigma, the index, is equal to the value of the polynomial at that point. Afterwards, that property is not true anymore. But the point is that now I keep giving you more non-zero. Every time I give you some more non-zero coefficient of this polynomial, you can get more roots in more integer roots in this, but only as many as there are non-zero coefficients of the polynomial. Right? Make sense? And this is really, so it's exactly equivalent to say it this way. If I sort of have if I think of really gamma as being sort of an unbounded communication, then it tells you sort of where the roots could be. So it sort of tells you more of a real-time thing. That the number of roots in between gamma sigma 1 to gamma sigma n or something is whatever the sparsity was in that interval. Okay. So if the statement of the lemma is clear, I'll prove it. This is the. Okay.
that's the joke.
Thank you, Nati. Yes.
Just checking.
So suppose this were false. Okay, so this is really the kind of core of the result. So let me. So suppose we're false, and so we'll take a smallest, so smallest in the sense of how many smallest contradiction in the sense not a degree, but in the sense of how many non-zero coefficients. Okay, so this is a polynomial gamma of x. Here it's where it has these non-zero coefficients, and we claim the lemma fails. So that means that we actually have s roots for this polynomial. And they have to be, so the t's are the location of the roots. They have to start at sigma 1. Actually, this has to be a strict inequality if you think about it. But anyway, they have to be, and so all these places, these are all. So to get a contradiction, So the claim is first thing I want to show you is that all the sigma j's are less than the tj's. So you don't get the jth root until you've had the jth non-zero coefficient. And well, suppose this were false. So there's some way of getting tj before or equal to sigma j. That can't happen right at the beginning, because, as I said, when you have the first non-zero coefficient of the polynomial, it immediately gives you a non-zero value also. That's just the singleton polynomial gamma choose, that's just, sigma choose sigma is 1. Okay? So j has to be at least 2. So now let's look at the sort of prefix polynomial that you would get if you just take j minus 1 term, non-zero terms. Okay, so this is some polynomial. Notice that j minus 1 is strictly less than s, so it has fewer non-zero coefficients. It's a smaller polynomial sort of in our ordering here. It agrees with these gamma. Now we use this hereditariness sort of. It agrees with the claimed polynomial over here on this segment, until it comes along a coefficient it didn't know about. So it agrees up till there. So that means it has all of these j minus 1 roots over here. And they're all bigger than sigma 1. But that's more than the allowed budget. So that was j minus 1 of them. Its budget, since s was a first counterexample, was only j minus 1 minus 1. So s couldn't have been minimal. Okay, so that's... we managed to boil this down to this. So that we're not done with the lemma. We've proven this claim that the roots only occur after the jth root only occurs after the jth non-zero coefficient. So we now know that fact. Okay, and now we write down the following matrix, which is called the binomial matrix. So if I sort of label the rows of the matrix by these numbers t sub I, where the roots were, and I label the columns of the matrix by the sigma j's, where the non-zero coefficients were, and I get this matrix full of binomial coefficients. And now we just notice the following thing, which is, again, this is one of the standard thing for coding theorists. If I look at the column vector gamma sigma 1 through gamma sigma s, I'm basically representing the polynomial that I care about as a column vector. And all you notice is that evaluating the polynomial is equivalent to multiplying this matrix by your vector. The claim was that those are all roots, so that means, so 0 is this matrix times gamma bar. Now this was certainly a non-zero vector, so this matrix has to have been singular. And then we bring in this amazing, beautiful fact, which if you haven't seen it, it's worth knowing, and I yesterday learned even more about it. But anyway, which is that this is a non-singular matrix. It has a beautiful combinatorial interpretation. Again, time permitting, I could show it. Which is that when you have these inequalities, you have an increasing sequence of sigmas, an increasing sequence of t's. You write down this binomial matrix, and if you have all of these inequalities, if sigma I is less than ti for all I, then this determinant is non-zero, and it counts non-intersecting lattice paths. Okay, again, time permitting, I'd love to show you that. And I'd love to show you even more. I just learned yesterday, sort of Klim realized this, and we figured it out. It's true. This actually follows. So this is a famous. This is a theorem from the 70s or 80s. Actually, is implied by a result of Polias from much earlier, but they didn't realize this connection, and I only realized it. Klim and I only realized it yesterday. So I can tell you two different beautiful proofs of this fact, but maybe not during the talk. Okay, so this proves our lemma, the sort of uncertainty principle. As a corollary, this code that I've defined for you achieves distance 1/2 in this loose sense. I mean, these are integers, so what do I mean? But I mean, the distance is clear. What we mean by rate is maybe not clear, but distance is really clear. I'm sorry. This is perfectly rigorous. Okay. Why? Well, because the number of roots and the number of coefficients trade off against each other. Okay. You can something I certainly won't say now during the talk is that you can. This gives us rate distance 1/2. You can get any distance 1 minus delta that you care about with the same idea, and the rate scales like delta squared.
Can
Yeah.
you just
Mhm.
to
Yeah.
help me organize it. So now you can tell us a code that's not kosher because it uses integers.
Yeah.
What does this code look like? Can you tell us where we are
Yeah.
at the moment?
Yeah, right. So now the code, I have a stream of integers, and
So we're talking about tree.
so if you want to think of it as a tree, then instead of being binary, it has
It's
degree z.
zero, right?
Yeah, it's a zero tree, and at every vertex I'll label with 2 vertices. So think of the value here being the value of the polynomial at 0 at the top level. First point I evaluate is 0. I tell you the value of the polynomial there. So I'm going to tell you, if everybody can read this small handwriting, I'll actually print that out, sort of systematic.
No, it's not a polynomial, it's actually a power series.
Yeah, it's really a power series because this thing can go on forever. So I tell you anyway the value of this function over here
Wait, it's a power series in the Newton basis.
in the Newton basis. That's crucial. That's crucial. Now it really, if you really want to think analytically, then you better.
So we're looking at this.
You're not expanding. It's not power series in the sense of expanding about a point
It's a formal power series, sum of A, J,
in the
X
Newton
to
basis.
J. Okay.
And now and this is again degree z, and I'll tell you what the value of the function at 1, and then the Newton basis coefficient that I need in order to achieve that, and I'll keep going. So this is the code, as it were. So okay. So now in whatever time remains, which I'm not actually sure what it is, I have to. There's some other things you need to do. I mean, actually, working over z is an idea that's been around for all of these 25 years and up till now. And so this lemma is really crucial and new, but there's still some things you need to do. There's still one nice idea that comes in. But the first thing, it's not yet. So the first thing is really easy. So we have to somehow talk about converting this to a finite alphabet, right? So the first thing to do is just to bound the size of the integers that you encounter. And it's not hard. This is just some elementary arithmetic to show that when I give you a bunch of z's, the gammas that you need to interpolate them at time t are bounded by 2 terms. One is just sort of, what size numbers you were already using. And then the other thing, and this is always the thing that's been so troubling, and is that, they also grow exponentially in t. Because you're hitting them by these binomial coefficients, and they let's grow exponentially in t. Okay, so there's a really nice thing that happens, which is that, so this seems like a terrible liability, this 2 to the t. It's certainly a liability, but actually there's a way of sort of turning this around and saying, if I have to absorb this factor of 2 to the t anyway, all I wanted to do was do a binary tree code. Actually, I can batch up a whole lot of binary coefficients into a number. I can batch up t of them. So I could basically make these numbers, I could batch up a whole long sequence and sort of allow myself to somehow be thinking of much larger numbers here without losing any efficiency at all. Okay. So So for binary tree codes, we wouldn't have needed anything but minus 1, 0, and 1, but we're gonna batch them together, and we'll get a weaker object, and we'll see how the complexity works out. So for every integer L greater than 1, there's this explicit tree code that's just the thing I've already described to you, essentially, that still achieves distance 1/2, but on alpha, so basically you're going to batch up things with like a lag that's like square root of the depth. If you want to go to depth L, well, actually sort of L squared, then I'll batch up L bits at a time. That's what's being said here, is that I'll take the alphabet 2 to the L, and I'll do L levels of such an alphabet, and there's essentially no loss relative to this factor that I already needed to pay. Okay. So the 3 comes because there was the whatever size the z's were, and then the gammas could be bigger than that by a factor of 2 to the L. So, okay. So what we sort of get for free from this, how much time do I, or what, am I in negative time? What's our?
It's negative time.
Oh, it's negative time. That's bad. So let me finish the construction. It'll take me a slide or two, and I'll, yeah. So this lag tree code is what you get by saying, suppose I actually had my binary tree code that I cared about, and I'll batch up, L levels at a time, and then I'll treat what I saw in those L levels as an integer of size at most 2 to the L, and then I'll apply my construction over Z. But of course, I have to wait till I have all of them. So there's a lag of L in this construction. A lag tree code is one in which I just say, look, I wait till like 16 times the lag has elapsed before I care about, I wait till the lag has elapsed before I care about distances. So I don't demand distance right away because I know I can't. I'm not just saying anything really. Okay. So if you allow huge amounts of lag, then this is just block error correcting codes. And I'm just reminding you of this sort of theorem of Shannon. But what you get from this construction is that, okay, this is really just expressing a little bit the kind of the idea we already have, is that once 2 strings x and y have split from each other, maybe in the middle of these, so these are batches of length L, if you wait just a few of the, if you wait for this lag, if you wait for like 16 of these batches to go by, and you impose an error correcting code with distance 5, 6, then you had distance 1/2 from the Z construction I described to you. Overall, you'll get distance 1/3. Okay, so the number's not important, but so that's what you do at a distance scale L. I haven't told you what L is. And the answer is, so the key thing in this, I'm sorry, I'm sort of now a little bit in a rush on time, is that the way that construction that I just described to you worked is there's a quadratic relationship between the lag and the depth of the tree that you would get. Okay, that was the natural relationship that came up from paying for this 2 to the L. Okay? But there's nothing stopping us, and that's what we do, from implementing this with all possible values of L from 1 up to the n that we actually care about. And each time you just square n and you implement the construction at that level. So you get these separate tracks. One at the very lowest, the first pair of tracks, you just repeat some tree code, bricklaying them, but then you go up by these squares every time. Okay, so that's the whole construction, and because you're squaring L every time you go through this process, the whole rate is log n. Okay, so that's, as I worried I wasn't going to get to Bill Watterson, but I just want to say what the main open questions are here. One is you'd like to efficiently decode these things. So we have these constructions. We don't know good decoding of tree codes, of any of our existing tree codes. So that's a major question. Whereas in the block coding world, for those who know, I mean, the state of the art is amazingly good. Here it's not. Here we don't know anything, essentially. Of course, we would really like to get a constant or anything, better. And then there are these other very different schemes that might give the ultimate. No.